All right, so this is chapter 15. Chapter 15, we're going to talk about acids, bases, and salts. So, the first thing we're going to talk about are acids and bases, and we're going to talk about kind of what some properties are. So, here are two very common acids. So, hydrochloric acid, HCl, breaks down into H+, which you are going to hear me refer to protons. When I say proton, I'm talking about an H+. And then it also turns into a chloride ion. Acetic acid, which is found in vinegar, that's what gives it that pungent smell. Acetic acid breaks down into that proton in the acetate ion. So some characteristics of acids are that they have a sour taste. That's actually how the word acid came about. It changes litmus paper from blue to red. And the way I always remember that is a lot of people think that acids are dangerous. Red kind of is a flashing warning that something's dangerous. So that's how I always remember that. Acids react with certain metals to produce hydrogen gas. They react with hydroxide bases to produce water, and they react with carbonates to produce carbon dioxide. Now, bases, one of the most common bases that we know or we use and talk about would be ammonia, NH3. So what happens here is NH3, ammonia gets a proton, and now it turns into the ammonium ion. We've got the carbonate ion there. And so if we add a proton to the carbonate ion, it can turn into the bicarbonate ion. And then sodium hydroxide is one of the most common bases as well. And so sodium hydroxide reacting with an acid is going to produce some sodium and some water. Now, some characteristics of bases are that they have a bitter taste, they feel slippery or soapy, they change a litmus paper from red to blue. The way that I remember that is that litmus or blue base, that's what I remember there. And many cleaning products and soaps contain bases. So the first type of base we're going to talk about is the Arrhenius acid and base. And so the Arrhenius acid is a solution that produces proton ions. Now, typically your formula is going to start with an H if you're an Arrhenius acid. So HCl is going to produce your proton, H+, plus chlorides. Now, an Arrhenius base is a solution that produces hydroxide ions. Now, your hydroxide needs to be within that formula somewhere to be an Arrhenius base. And so if we think about sodium hydroxide, when we put that in water, it turns into a sodium ion and a hydroxide ion. The next type of acids and bases we're going to talk about are Bronsted-Lowry acids and bases, and this is going to be the one that we focus on quite a bit. So a Bronsted acid is a proton donor, meaning that it somehow has to have a proton that can donate into something else. So HCl, you get that proton that can be donated. If we think about carbonic acid, you've got a proton that can be donated. Okay, and so when we take away that proton and we now get, for example, this one would get a Cl minus. That Cl minus is the product. That would be what we call the conjugate base. So these are opposites of each other. The acid is HCl, and then when we take away that proton, the new product that's left over is called the conjugate base. Now, a conjugate base is always going to have one fewer hydrogen atom, and it's going to have one more negative charge than the original. Now, if we think about a Bronsted base is a proton acceptor. So one of the more common ones that we think of is NH3. So this would be our base. When we add a proton to it, it's going to turn into NH4 with a positive charge. So this was our base. This is what we call our conjugate acid. Okay, so again, up here, your acid was your HCl, and your conjugate base was our chloride ion. And then down here, the base would be our NH3. When we add that proton, it now turns into NH4 positive. So that's our conjugate acid. Now again, conjugate base is going to have one less hydrogen than the original, and it's going to have a more negative charge. And then your conjugate, if we think about bases and conjugate acids, your conjugate acid is going to have one more hydrogen atom, and it's going to have a more positive charge. So if we take a look at some examples here, we've got water turning into hydroxide. Okay, so Water would be our acid in this case, and the hydroxide is our conjugate base. Remember, they're opposite terms from each other. So if you know what the acid is, the conjugate base has one less proton and a more negative charge. And then for the base, which is ammonia, NH3 in this case, when it gains a proton, its new product is called the conjugate acid. So the base takes a proton, and when it becomes that new product, it's now the conjugate acid. So this is what it looks like all together. If we take water and ammonia, it's going to turn into hydroxide and ammonium. So again, your what's happening here is that your water is donating a proton. Okay, so water is going to donate a proton to the ammonia. That's going to turn it into NH4 plus. And so since HOH lost a proton, it's now just OH minus. And so we get water as an acid turning into hydroxide. So acid, conjugate base. And then our base, which is our ammonia, now adds a proton. And so once it adds a proton, it is now called the conjugate acid. Now, to practice kind of figuring this out, here are a few examples. So if we react hydrochloric acid with water, we're going to get H3O plus. H3O plus is called hydronium. So if you ever hear me say hydronium, H3O plus is hydronium. You'll sometimes see H3O plus and sometimes you'll just see H plus. They're both the same exact thing. So if you ever see H plus, it's the same as saying H3O plus. They're just written a little bit differently. Okay, so if we put hydrochloric acid into water, you're going to get that hydronium ion and you're going to get that chloride ion. So this is our acid. And then when it turns into Cl minus, this is called our conjugate base. Now, if we take our acetic acid and we remove that proton, it now turns into the acetate ion. The acetate ion is going to be our conjugate base because this was our acid. Okay. Now, if we take a look at some of our bases, ammonia is our base. When it takes a proton, it now turns into NH4 plus ammonium. This is our conjugate acid. Because this was our base, that's our conjugate acid. And then lastly, hydroxide. If we take hydroxide and we take a proton, it now turns into water. So this was our base. This is our conjugate acid. Now, in each and every single one of these, we also have an acid or a base. So in the first one, this was our acid. This was our base. And so since this turned into Cl minus chloride, this is our conjugate base, opposite. And then this turned into that, so that's our conjugate acid. Okay? And this was our acid. This one was our base. Our base turned into that. That's our conjugate acid. Our acid turned into this. That's our conjugate base. Down here we've got base. Water's acting as an acid. That turns into our conjugate acid, NH4 plus, and our acid of water is turning into our conjugate base of OH minus. Now, figuring this out, you will, the last few that we just looked at were waters. And so you're always going to, in those cases, if you're reacting with water, it's going to give you either an H3O plus or an O minus. But we can actually have two substances react where neither one of them is water. And so to figure out your conjugate acid and base, we need to actually take a look at the whole picture. So if we take a look here, since we have F minus and H2SO4, what I want you to notice right away, F minus doesn't have any protons on it. It doesn't have an H on it. So if it doesn't have an H on it at all, we know right away that's our base, making this our acid. If we take a look, we can also see the other reason we can tell that this is the base is because it gained a proton. It gained an H plus there. So it turned from F minus into HF. And then this one here, you can see that it lost a hydrogen. So that can also tell us it's the acid. So base turns into its conjugate acid, and acid turns into the conjugate base here. Okay, so that's how I would go about it. Just take a look at what's happening from start to finish. Whichever species gained a proton, that would be our base. Whichever one lost a proton, that would be our acid, and then you can figure out the opposites. So the base turned into a conjugate acid, and the acid turned into a conjugate base. So I want you to take a look and practice on this next example. So we've got two here. We've got H3PO4 plus water is going to give us H2PO4 minus plus H3O plus, and then H2O plus NH4 plus giving us NH3 plus H3O plus. So for all of these, what I want you to do is I want you to figure out what the acid, the base, the conjugate acid, and the conjugate base are. So all four are going to be in each one used once. Your acid and base are on the left side, and the conjugate acid and the conjugate base are on the right side. So here's our answers. In this first one, H3PO4 is our acid because you can see there that it's giving a proton up. It's giving an H up to water. And so since it gave an H up, it's the acid. Since H2O accepted that proton, it now becomes the base. And so H3PO4 without hydrogen is our conjugate base. So remember, our acid turns into our conjugate base. And then whatever was our base, it turns into the conjugate acid on the product side. Now our next one, if we take a look there, the NH4 plus is giving a proton up to H2O. And so since it's giving that proton up to H2O, our H2O is our base. It's accepting a proton. And our acid is giving it up. So then on the product side, if we take a look, NH4 plus without a proton is our conjugate base, and H3O plus, our hydronium, is our conjugate acid. So you have to know how to identify these different species. The last type of acid and base is the least common. This would be called our Lewis acid and base. So Lewis acid is a species, which could be a molecule or ion, that can accept a pair of electrons. So we were just thinking about protons, H pluses in the past. Now we're thinking of electrons. So the Lewis acid accepts the electrons, and the Lewis base donates the electrons. Now when this formation happens, we get what's called a coordinate covalent bond, and that's what's created when that Lewis acid and base meet. So if we take a look down here, your Lewis acid is the one on the right, and this one is the Lewis acid because it has a spot that it can accept a lone pair of electrons to. Your Lewis base has to have a lone pair of electrons that it can donate there. And so once that donation happens, then you get this bond formed between them. So here's some examples of some different Lewis acid and bases. So you'll see here what's happening is that we have a lone pair of electrons bonding to our boron. And so you form this bond here. This one, we're taking two ammonias and giving them to silver. So really what you're seeing here is you're seeing another one over here. That's what the two here is telling us, is that we have another one that's actually over here. And so now that I've drawn two, what's going to happen is that lone pair will be donated. That lone pair will be donated. And so you get this bond here and that bond there. And the last one here, what we're doing is we're taking a lone pair of electrons, donating it to the sulfur here, and so we make this bond right there. All right. So those are the three types of acids and bases. Arrhenius acid and bases are the most kind of common that you can usually just see. The Arrhenius acid starts with an H. The Arrhenius base has an OH in it. The Bronsted acid is a proton donor, and the Bronsted base is a proton acceptor. And then down here with Lewis acids and bases, the Lewis acid accepts a pair of electrons, and the Lewis base donates a pair of electrons. So in acid reactions, acids can react with metals that are more active than hydrogen in the activity series to produce that hydrogen. So if we react hydrochloric acid and zinc, we're going to produce hydrogen gas and zinc chloride. We can also have acids reacting with bases. So typically this is going to be our Arrhenius acid and base, starting with an H, ending with an OH. So these, what they're going to do is produce a salt and water. So salt is not always sodium chloride. It's not always the one that we put on our food. It could be something like potassium chloride here. And so we're going to always get some sort of salt, which is an ionic compound, and then some water. So talking about salts, salts are any ionic compound with a cation and an anion. And salts are formed when acids and bases react and water is being produced as a byproduct. So let's say we have calcium hydroxide plus sulfuric acid. We're going to get calcium sulfate as our salt, and then you can see that we produce some water as well. The next one, if we have lithium hydroxide and carbonic acid, we're going to get lithium carbonate and we're going to get some water. So both of these ionic products here, these are our salts, and then we've got our water. So we're going to talk about electrolytes. Electrolytes are substances that dissolve in water and undergo a physical or chemical change to produce ions. So electrolytes, you have to have ions being produced in order to be an electrolyte. A non-electrolyte are substances that do not produce ions when dissolved in water. So when we think about electrolytes, you're probably thinking about Gatorade or Pedialyte, something like that. And your electrolytes are just things that we dissolve within solution so that they are ions so that our body can use them. Your non-electrolytes, your body can still use them. They just don't split apart when they're in water. So some common electrolytes would be your acids, bases, or other ionic compounds. So we've got things like hydrochloric acid, sodium hydroxide as a base. We've got potassium iodide is just a salt. Ammonia is another example of a base. So those produce ions when they're in solution. Your non-electrolytes do not produce ions. They don't break apart. So oxygen doesn't break apart. Methanol does not break apart when we dissolve it in water. Sugar does not dissolve when we put it into water. Same with ethanol. The big dead giveaway, usually for a non-electrolyte, is going to be that it contains carbons and hydrogens of some sort, or it's a molecule like oxygen. So your electrolytes, acids, bases, and ionic compounds, and then non-electrolytes are typically molecules or they contain carbons and hydrogens. So to create electrolytes, you need to go through this process of dissociation. Now we've seen this picture up in the top right. Again, remember that the hydrogens on our water are partially positive, the oxygens are partially negative, and so the hydrogens are going to be attracted to the negative chlorides, and then the oxygens are going to be attracted to the positive potassium in that case. Down in that image down there, you can see those waters start to attach to those ions and pull them away. So originally that looked like a grain of salt, and now it's starting to pull those ions away, and it's going to make it a clear solution in the end once all of those ions are separated from one another. We also have ionization. So ionization happens when a substance changes into an ion. So for example, we've got our acetic acid. Pure acetic acid, we can buy it as pure acetic acid. That is a non-electrolyte, meaning that that liquid does not have ions in it. But as soon as we start to mix our pure acetic acid into water, what you're going to get is you're going to get that acetate ion, C2H3O2 with a minus charge, and you're going to get that hydronium ion, H3O+. And that hydronium ion gives us that acidic characteristic when it's in water. So ionization just happens when ions are formed and the solution then becomes an electrolyte. Within electrolytes, so we've got electrolytes and we've got non-electrolytes. Within electrolytes, we've got two categories. We've got strong electrolytes and weak electrolytes. So our strong electrolytes, essentially 100% of the dissolved substance generates ions, meaning they all completely break up. And so in order to be a strong electrolyte, you have to be a strong acid, a strong base, and most of our aqueous salts, meaning most of the salts that dissolve in water will be strong electrolytes. Our weak electrolytes, only a small fraction of the dissolved substances generate ions, and those will be weak acids and weak bases. So here's some examples. Our strong electrolytes would be like our strong acids. We've got hydrochloric acid, hydrobromic acid, hydroiodic acid, and then that next one's called perchloric acid, nitric acid, and sulfuric acid. So those are the 6 strong acids. We've got strong bases, which would be sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. And then we've got most of our salts. These are just 3 that I listed. There are tons and tons more. of ionic salts that dissolve in water. And so essentially what that means is that those substances there are going to completely break into their ions. They're not going to stay together in the formula that you see. They're going to break apart into the ions that are connected to each other. Your weak electrolytes are our weak acids and our weak bases. That first weak acid is called acetic acid. That next one is called carbonic acid, and that last one is hydrofluoric acid. Those are the three common weak acids. And then the weak base that you need to know is ammonia. NH3 is called ammonia. So what does non-electrolyte, strong electrolyte, and weak electrolyte actually mean? Well, non-electrolytes do not conduct electricity. They're non-conductive. If we wanted to try to get a charge forming between them, they don't produce a charge because they're all molecules. They don't break apart into positives and negatives. So a non-electrolyte will not conduct electricity whatsoever. A strong electrolyte is going to conduct electricity very well. So you can see that light bulb is lit up pretty good there. And then the weak electrolyte there conducts electricity, but not super well. And so acetic acid, a lot of the acetic acid is still represented by these double bubbles. And so that is C2H3O2. And then only some of them break into H plus. And then this is C2H3O2 minus. So only some of them break up into those ions. Most of them stay together. Okay. Versus over here, if this was sugar, all of the sugar can dissolve. It just won't create ions. So you don't conduct any electricity. Now, when we break into ions, they're going to produce specific ions. So sodium hydroxide is going to produce the sodium and 1 hydroxide ion. So there's 2 ions per formula unit. That's what Fu stands for. The next one, calcium nitrate, we're going to produce 1 calcium ion and 2 nitrate ions. You can see that based on that the subscript down below the nitrate. So we get 3 total ions per formula unit. Again, formula unit just means these formulas here, okay? So the ionic formulas. When we dissolve something like iron chloride, iron 3 chloride, you get 1 iron 3 plus ion, and you get 3 chloride ions for a total number of 4 ions. Now, why do we care about that? Well, if we're going to dissolve 1 mole of that substance, you're going to get a mole per each ion that's in solution. So if I get 1 mole of sodium hydroxide dissolved in a solution, you're going to get a mole of sodium and you're going to get a mole of hydroxide. If you dissolve calcium nitrate into solution, you're going to get 1 mole of calcium ions and you're going to get 2 moles of sodium ions. Nitrate ions, my bad, NO3. So you're going to get 1 mole of calcium and 2 moles of nitrate. And then if we take iron 3 chloride and dissolve it in water, 1 mole of that will turn into 1 mole of iron 3 plus and 3 moles of chloride. So we get 4 total moles of ions. Now, the same thing can be done for molarity. What you can do is you can take the original molarity and multiply it by the amount of ions produced. So if we dissolved 1 molar sodium hydroxide, you're going to get 1 molar of sodium and 1 molar of hydroxide. Let's say we're only dealing with a half molar of calcium hydroxide or calcium nitrate. If we have half mole of calcium nitrate, you're going to get a half molar of calcium ions, but we're going to get 2 moles of sodium or nitrate ions. Okay. And then lastly, let's say we made a 2 molar solution of iron chloride. You're going to get 2 molar of our iron, but 6 molar of our chloride. Again, you have to figure out how many ions are going to be produced. You have to take a look at your original concentration and then multiply it by that. So in these examples here, I want you to determine if they are a strong electrolyte, a weak electrolyte, or a non-electrolyte. If it is a strong electrolyte, meaning a strong acid, strong base, or an ionic salt, then you need to figure out the molarity of each ion. Otherwise, the molarities are pointless. You don't have to deal with them for the weak electrolyte or the non-electrolytes. All right, number 1 is a non-electrolyte. That is glucose. Glucose will dissolve in water. It just won't create ions. The next one is sulfuric acid. That is a strong electrolyte. you're going to get 1.6 molar of our H plus and only 0.8 molar of our sulfate ions. So in there you get two H pluses and you get one SO4 that sticks together. In your next one, that is also a strong electrolyte. That would be a salt. You're going to get 1.5 molar of our iron because we had two irons breaking apart into ions, but we're going to get 2.25 molar of our sulfate because we took 0.75 times 3. That gets us that 2.25. Your next one is carbonic acid. That's a weak electrolyte. Ammonium is a weak electrolyte. And then the last one is methanol. That is a non-electrolyte. That will dissolve in water, but it just won't break apart into ions at all. So when we think about breaking into ions or turning into ions, we can talk about the auto-ionization of water. Let's break that word down. Auto means it happens automatically. It's always going to happen. And ionization meaning we're taking a substance and turning it into ions. So this always happens. In water, you constantly have what are called hydronium. We can also think of this as a proton. And then hydroxide. So you can see it written both ways. Up at the top, you can see that water can turn into hydronium and hydroxide, or water can be turned into a proton and hydroxide. Remember that these two things are equal to each other. H3O plus and then the H plus are the same exact thing. They just are represented a little bit differently. So this is constantly happening. In water, we're constantly getting these protons or hydroniums and the hydroxides. And so at 25 degrees Celsius, which is kind of our normal temperature, the equilibrium expression, okay, I know we haven't talked about equilibrium, but essentially what that means is that at any given moment in time, the concentration of the protons and the hydroxides is equal to 1.0 times 10 to the negative 14th. So what you're going to see on your exam reference doc is down here at the bottom, okay? And what that means is that if you take this number, that number is always equal to the concentration of protons times the concentration of hydroxide. Anytime you see a bracket, bracket equals molarity, okay? So if we know the molarity of one of those, let's say we know the molarity of H plus, we can plug that in. So if we know the concentration of our protons, we're going to solve for hydroxide. And we can actually plug that value right in there, okay? And so we would get the concentration of our hydroxides. That's how we use this. Now, if we want to take a look at an example, what is the proton concentration if the hydroxide concentration is 5.6 times 10 to the negative 19th? So this expression is the one that you will be given on your exam, okay? And you need to be able to use that and rearrange it to solve for some different products. So in this one, we know the hydroxide. Okay, so this is what we know. This is what we're trying to get to. And so we're going to divide that underneath the KW expression. And so we get 1.0 times 10 to the negative 19th divided by 5.6 times 10 to the negative 9th. And the hydroxide concentration is 1.8 times 10 to the negative 6th. Now, in these calculations, make sure you're using that EE button on your calculator. Otherwise, you most likely will get these questions wrong. So once we determine the concentration of the proton and hydroxide, we can figure out what kind of solution it is. So if they were equal to each other, that would be a neutral solution. Equal means that they have to be the exact same number with the exact same exponent on the 10. If you have more protons than hydroxides, then it's acidic. If you have less protons than hydroxide, then it's basic. That means you would have more hydroxide than protons. That's the other way to look at it. So the higher the proton concentration, the more acidic. So the more protons, the more H pluses you have, the more acidic it is. Now in that previous problem, the proton concentration was 1.8 times 10 to the negative 6th, and the hydroxide concentration was 5.6 times 10 to the negative 9. Remember that a smaller negative number means that it's a bigger number. So times 10 to the negative 2 means that it's a lot closer to being a whole number than something like times 10 to the negative 10. that has a lot of zeros in front of the numbers, making it a really small decimal. So you just have to remember that with scientific notation. So the concentration of hydroxide ions in a certain household ammonia cleaning solution is 0.0025 molar. So that's your concentration in your bracket, OH minus. I want you to calculate the concentration of your protons at the temperature of 25, and then determine if that's acidic, basic, or neutral. All right, so we always know that equation Kw equals our proton times hydroxide equals 1.0 times 10 to the negative 14th. We're solving for our proton here, so we're going to divide by our concentration of our ammonia, which is 0.0025 molar. Then we figure out that the proton concentration is 4 times 10 to the negative 12th. Since the proton concentration is less than the hydroxide concentration, the solution would be basic. Now, we're going to talk about pH and pOH here in just a sec. So pH really tells us how much proton concentration is in solution. And so as the concentration of protons increases, the pH decreases. These are opposites of each other. So if you have a lot of protons in solution, that means you're probably an acid, which means you have a low pH. Now, in neutral solutions, your pH is equal to 7. Okay? Again, I'll repeat to you. If your pH is 7, that means you're neutral. If your pH is less than 7, meaning usually it's somewhere between 0 and 6.999, that would be an acidic solution. If your pH is greater than 7, meaning 7.001, all the way up to typically around 14, that would be what we call basic. Okay, so to calculate your pH, you're going to take the negative log of the proton concentration, H+. So if we know the molarity of your H+ right here, you're going to take the negative log of that. So you're going to need to press the negative button on your calculator, and then you're going to have to find the log button on your calculator, and typically it's going to put a parenthesis right after. Then you can put your proton concentration right into your calculator after that. So again, you're going to need the negative button, then the log, and then you can put your concentration in there. Now let's say we know the pH and we're trying to find the proton concentration. We can take 10 to the negative pH to find our proton concentration. So let's say that the the pH was 6, so 10 to the negative 6 would be our proton concentration if the pH equals 6. Okay, so that's how you deal with that there. Now, pOH is very similar. pOH is just dealing with the concentrations of hydroxide instead of protons. So the pOH is the negative log of our OH minus concentration. So again, you're going to need to press the negative button. Then you're going to need to type in the log button, which typically puts a parenthesis, and then you can type in whatever you need to. Now, the hydroxide concentration can be figured out if we know the pOH. We're going to do 10 to the negative pOH to find that OH minus concentration. And then this other equation is also given on your sheet. Now, what this does is if we take our pH and our pOH, those two add up to 14. So let's say that my pH was 3, and I'm trying to find pOH. So to find pOH, I would take 14 minus my pH. So I'm taking 14 minus 3, so my pOH is 11. Okay, so you can use all 5 of those that are in the boxes. Those are all on your equation sheet. And you're going to have to use them in different ways to get around to different things. So here's some different examples of substances with different pHs. Gastric juice, meaning the juice within your kind of intestinal system, is pretty low. It's got a pH of around 1.5. Lime juice is pretty acidic. That's got a pH of around 2. Coffee is acidic, around 5. Now, pure water is 7. So that's a neutral solution. But you'll take a look, rainwater is slightly acidic and ocean water is slightly basic. It all has to do with what's dissolved into that water. Some other bases would be your blood is slightly basic. It's around a 7.4, I believe. Your baking soda is basic. Milk of magnesia, which you might help to take for your stomach, that's basic. Your ammonia and your bleach used for cleaning, those are basic as well. Now, the lower the pH, the more acidic it is. The higher the pH, the more basic it is. Now, your pOHs are opposite. So the lower your pOH, the more basic it is, and the higher the pOH, the more acidic. So doing these calculations, let's say that I was starting with just this value here. Let's say that this was the only value I was given. You can go about solving the rest of those boxes in many, many, many different ways. The way that I choose to do it might be different than the way you choose to do it, which might be different than the way your lab partner does it. It's all totally okay as long as you're using the equations the correct way. So what I'm going to do here is I'm going to first calculate the pH. And so to find the pH, I take the negative log of my proton concentration. So I take the negative log there, and I figure out that my pH is equal to 4.5. From there, I take that and I use the equation that pH plus pOH is equal to 14. And so I'm going to take 14 minus my pH to find my pOH. So my pOH at this point is 9.5. And then lastly, I'm going to go use that 9.5 of my pOH to figure out my hydroxide concentration. And my hydroxide concentration here is 10 to the negative 9.5, or 3.2 times 10 to the negative 10th. Because my pH is less than 7, I'm acidic. Okay? So let's try this example here. The concentration of proton ions in a bottle of table wine was 3.2 times 10 to the negative 4th molar right after the cork was removed. Only half of the wine was consumed. The other half of it, after standing in the air for about a month, was found to have a hydrogen ion concentration, or proton concentration, equal to 1 times 10 to the negative 3rd molar. I want you to calculate the pH of the wine on both of these occasions. So you're solving pH just twice. Simple pH just twice. All right, here would be your equation. pH is the negative log of your proton. So at opening, the pH was about a 3.5, and then after standing open for a while, your pH was a 3. This next one, in a sodium hydroxide solution, the hydroxide concentration is 2.9 times 10 to the negative 4th molar. I want you to calculate the pH of the solution at 25 degrees Celsius. So what I need you to do is determine, or what I would do, I guess, is determine the pOH using the hydroxide concentration, the OH minus concentration. Once you know the pOH, remember there's that nice handy calculation, pOH plus pH equals 14, so you can solve for your pH at that point. So here's the answer here. I'm going to find my pOH first. My pOH is my negative log of my OH minus. So the negative log of 2.9 times 10 to the negative 4th gives me 3.5. And then my pH is 14 minus my pOH, which gives me 10.5. Now, a pH of 10.5 is basic because it's above 7, and that makes sense. Sodium hydroxide is a strong base. All right, so this question here says that the pOH of rainwater collected on a certain region of the northeastern United States on a particular day was 9.18. I want you to calculate the proton ion concentration, or brackets H plus, of the rainwater. So my plan of attack here for you would probably be to find the pH using the same method we just did in the previous problem, and then you're going to use the equation 10 to the negative pH equals proton concentration to solve for that proton. All right, so here's our answer here. If I know my pH and my pOH, I can take 14 minus my pOH to find my pH. So my pH here is 4.82. That tells you it's pretty acidic there. And so then to find my proton concentration, I'll take 10 to the negative pH. So 10 to the negative 4.82 is going to give me an ion concentration of 1.51 times 10 to the negative 5. So the next thing we'll talk about is neutralization. Neutralization reactions happen when an acid and a base react to form salt in water. Remember, salt doesn't have to be your traditional sodium chloride that we put on our food. It just has to be an ionic compound that's formed from an acid-base reaction. So the normal reaction is going to look something like this. We've got two hydrochloric acids reacting with calcium hydroxide. The calcium and the chloride are going to combine to form calcium chloride, and we're going to get two waters. We can break each of the ions down to think about how the double replacement actually happens. We've got two protons plus two chloride ions from that hydrochloric acid. We've got calcium and hydroxide. And so the protons and hydroxides are going to come together to form that water, and then the calcium and the chloride are going to come together to form that calcium chloride. Now, we use titrations in acid-base chemistry. And now titrations, we're going to be using burettes. Burettes are extremely precise. They go down to the 0.01 place, so the hundredths place. And so what we do here is we're going to use a known concentration that could be using a known mass of a solid, or it could be using a known concentration and volume of something. And then we're going to titrate it with an unknown. So you have to know the volume of one thing, and then usually there's an unknown concentration of that. And then we need to use either the volume and concentration of one thing, so a known concentration and a known volume of one thing, or you can use the mass of a solid to figure out the concentration. So when we do titrations, we're really thinking about the equivalence point, and that's the point in the reaction where all the starting material has reacted to form the products. So in an acid-base reaction, the moles of the acid and the moles of the base are equal to each other at that equivalence point. So if we started with a solution that contained 1 mole of hydrochloric acid, the equivalence point would happen after we added 1 mole of base. In a titration, we typically use indicators. An indicator changes color based on the pH. And so the most common indicator that we use is called phenolphthalein. Now, phenolphthalein is clear in acids, which is a pH of less than 7. I think actually the pHs that it changes color at is around 8. But phenolphthalein is clear in acids, but pink in bases. And so when we do the titration, you're going to try to get that light pink color. You don't want to overshoot it and get a really dark pink color. You're just going to shoot for a very light pink color. When that light pink color has been hit, that tells us that we have gone from an acid to a base, or from a base to an acid, whichever way you look at it. And so that's the point that we're trying to get to. All right, so if we are dealing with liquids and liquids for our titration, you are going to know the volume and concentration of one thing, and then you'll only know the volume of the other thing. So we would start the stoichiometric problem with the volume of the substance that you know the concentration of. Once we have that started there with volume of the substance that we know the concentration of, you can use that volume to get to moles using the known molarity. Once we have moles of the substance that we know the most about, we can go from moles of that to moles of the unknown. And what we need to do is stop there. So stop with moles of the thing you're trying to find the concentration of. Then you're going to divide that mole answer by the liters of that substance. So you would have to know the volume of that substance. You have to convert that to liters. So you would divide those to find the molarity. Here's a sample problem here. Determine the molarity of a 10 milliliter sample of sulfuric acid that was titrated with 22.54 milliliters of 0.120 molar sodium hydroxide. So you can see there's my balanced equation. I'm going to start with the milliliters of sodium hydroxide, get it into liters, get it into moles of sodium hydroxide using my molarity. And then I'm going to use that mole-to-mole ratio to get me out of moles of sodium hydroxide into moles of sulfuric acid. I need to stop there. The tendency is to somehow keep going here with the stoichiometric problem. Stop there with moles. And then you're going to take your volume of that sulfuric acid, get it into liters. So 10 divided by 1,000 is 0.01. And then you take your moles divided by that 0.01 to get our 0.541 molar sulfuric acid. This problem here is asking what is the concentration of calcium hydroxide solution if 25 milliliters of the calcium hydroxide was neutralized, meaning that it came to reaction with 12.45 milliliters of 0.750 molar hydrochloric acid. Write the neutralization reaction first, meaning react calcium hydroxide with hydrochloric acid. Remember that you're going to get a salt and you're going to get some water. So here's our reaction. Calcium hydroxide plus 2 hydrochloric acids gives us calcium chloride plus water. And here's our math. We're going to start here with our volume of our hydrochloric acid. We start there because we know the volume and we know the concentration of hydrochloric acid. Don't try to start with just a volume of calcium hydroxide. That's not going to lead us anywhere. So out of milliliters of hydrochloric acid, sorry, that's supposed to say milliliters there. Oops, sorry, my bad. That's supposed to say milliliters to start, not liters, milliliters. And then we get it out of milliliters into liters, out of liters into moles, out of moles into moles of calcium hydroxide. You need to stop there. We need to get our volume of calcium hydroxide into liters. So you take your moles divided by your volume in liters, and we get our molarity, 0.187 molar calcium hydroxide. This does not change if we start with a mass. A lot of times we might use what's called KHP, which stands for potassium hydrogen phthalate. And so we might use that, which is a solid. If we measure that out in grams, the process doesn't change a whole lot, except that you're going to start with grams, go to moles, use the mole-to-mole bridge to get us into moles of the base that we're trying to figure out, and divide that by the liters of the base. So in this case, what's the concentration of sodium hydroxide? If it took 25 milliliters of the sodium hydroxide to neutralize 0.125 grams of KHP. So we know the mass of the KHP. We're going to start there, get it out of grams into moles using the molar mass of that. And in this case, it was a 1-to-1 mole ratio. So we get the moles of the sodium hydroxide there. We're going to get our volume of the sodium hydroxide into liters, then divide it, and to get our molarity. The other type of calculation you could see here would be trying to figure out when the equivalence point is reached. You start with the volume of the species that has the known molarity. You're going to work through that stoichiometric problem to determine the volume of the species that we have a molarity for, but not a volume. Meaning we're going to go from volume, let's say that A, we know a volume and a molarity. So we would go from volume of A to moles of A to moles of B. And so B, we would know the molarity of, we just don't know the volume of. That's our question mark. So moles of B, and we can get to volume of B using that molarity there. All right, so for this problem here, we're being asked how many milliliters of the 0.150 molar nitric acid it would take to neutralize 33.65 milliliters of the 0.125 molar barium hydroxide. For this one, since we know the volume and molarity of barium hydroxide, that's where we start. We're going to get it out of volume into moles using the molarity there, out of moles of barium hydroxide into moles of nitric acid using the mole-to-mole ratio. And then finally, we're going to get it out of moles of nitric acid into volume liters using the molarity that we know for the nitric acid. So 0.150 moles goes, the 0.150 goes with moles and 1 goes with liters, and then out of liters into milliliters. And then our last practice problem here, how many milliliters of 0.140 molar strontium hydroxide would it take to neutralize 16.25 milliliters of 0.350 nitric acid? You need to write the neutralization equation first. Remember, you're going to get an acid plus base gives us salt and water. So here is our answer. We're starting with the nitric acid because that's what we know volume and we know molarity of. So get us out of volume into moles using our molarity. A mole-to-mole ratio is going to get us out of moles of the nitric acid into moles of strontium hydroxide. And then finally, we're going to use that molarity of the strontium hydroxide to get us out of moles into liters, and then liters to milliliters there at the end.